Okay, again, welcome. Today is November 5th. We are getting into now magnetism, basically. I lost count. I think it's chapter 23 or 24 or something. Chapter 24, yes. So we're getting into magnetism today. For those who are in Physics 11, we have done already an experiment on it, and we have an understanding of it. And actually, I can't wait for you guys to build your motors so that you show that how it's working, okay? For those who didn't or are not sitting in Physics 11, this is a concept that we're going to introduce today. So one of the things that, let me first of all share with you the screen that we normally share in here. So again, we're going to talk about the magnetic force, okay? And the fact that the magnetic force is always perpendicular to the velocity, so that you know, okay? So when you have a charged particle moving inside a magnetic field, it's going to be subject to a force. So the magnetic field will exert a force on a charged particle that is moving inside of it. And from there, the direction of the force is perpendicular to it. Now, it happens that two magnets can exert forces on one another, okay? I have two magnets in here. If I separate them, because one of them, as you can clearly see, is red and the other one is blue. By convention, the red is positive, or a north pole, and the blue one is a south pole. So if I put them together, now they attract to one another and they're stuck, okay? If I reverse the polarity in here and have them the same poles, they repel. So this is in a nutshell what the magnetic force is. And people, of course, were fascinated with magnetism for a long time, and you can basically I mean, you would be tempted to levitate for it. So if you can have it suspended in here, so it can levitate. This is one of the things that everybody, when they are young, they play with magnets. Okay, magnets come in different shapes and forms. Okay, so ever since magnetism was discovered, people were fascinated with it. Some of it was some of the people associated with magic, other people associated with other things for properties of some of the materials. I was in San Diego a long time ago, and I met this lady, and she was telling me about this something that she believed in. I don't know, it's one of this new wave thing that people have a new faith in things, and I don't have a problem with that. I mean, that's a person, his belief is his belief. You can't really dispute that. But the minute she mentioned electromagnetism and magnetic force and things like that, I became very doubtful. A religion or a faith that is based on that, there is science behind it. So I can't really, I can't believe that after that, because I know what's going on in there. Okay. So anyway, so it was associated with some sort of like basically myth and all kinds of things before, but now we understand what magnets are. Actually, we have a very good idea what magnets are, so we know how they work, and it's really one of the it's entangled, and this is item 1 of the discussion, actually, with the electric force. Okay, electricity and magnetism. I don't have a quarter in here, otherwise I would show you the example. It's the two sides of the same coin. So quarter, for example, has face and has, what is it, the back of the face, what do you call them? Heads and tail, okay? This is the same story between magnetism and electricity. Both of them, they are the two faces of the same phenomenon. Now we know what it is called. It's called electromagnetism, okay? So the phenomenon in question is electromagnetism. So what is a magnet? What is magnetism? It's the other side of electricity in what we know today as electromagnetism. So this is item 1. Does everybody get it? So magnetism and electricity are two sides to the same phenomenon. Okay. As a matter of fact, sometimes a magnetic behavior can exhibit itself in electrical behavior, and sometimes it flips back to a magnetic behavior. So the two are one thing. You guys understand this point? Yes, no? Okay, so this is item 1. Thank you, Josh. Okay. Mr. Maxwell is the one who basically summarized all of the equation of electricity and equations of magnetism and put them together, and they became the theory of electromagnetism. And he did a tremendous thing in the 1880s, just before he died, basically, where he put all of this two phenomena together, and he added to them as a bonus optics, which was a mystery by itself. For example, light itself basically was another mystery, so it was added to that mixture. Not only that, there was another kind of optics that was not understood at that time, and people believe it's really related to geometrical optics. Basically, when you shine a light on a specific point, it's going to reflect on all of the other things. So light with both behaviors, the reflection and the refraction, and also light with the phenomenon of waves, which was doing patterns of interference and things like that. Mr. Maxwell took all of this four stuff and put them in a bunch of equations, called them electromagnetism. So electromagnetism unifies electricity, magnetism, geometrical optics, which is used for the lenses and glasses and cameras and seeing and all of that, and another kind of optics also that was known at that time, and that was so-called wave optics. Wave optics has to do with the diffraction and interference patterns and things like that. He put all of this four into just one theory. This work inspired actually Mr. Einstein to see if he can unify not just the theory of electromagnetism that Mr. Maxwell did, but also the gravity that Mr. Newton and he himself actually improved on, and also the emerging at that time, during the time of Mr. Newton, the emerging science of quantum mechanics. Unfortunately, he passed away in 1955 without realizing his dream. And ever since, people are really, physicists everywhere are really after this idea, trying to come up to finish Mr. Einstein's work. Until today, nobody succeeded, okay? So this is just to follow on what Mr. Maxwell did and what he inspired later on. He inspired Mr. Einstein and many, many people after that, and it's still an ongoing thing. So electricity and magnetism, per Mr. Maxwell's theory, are two sides to the same thing, okay? So again, we're going to talk about magnetic poles, and that is the other thing. We have all magnets, they seem to appear in two different poles, okay? Every magnet that you have in nature has a north and a south, okay? Somebody said, okay, how about this? I'm going to go and cut it in here, right in the middle, okay? Cut it with pliers or whatever you have equipment in there. Then I will have the north by itself and the south by itself. Is this possible? What do you guys think? Can I isolate the north by itself and the south by itself? No, absolutely not, okay? So what happened then? If I isolate them, what do I end up with? If I cut them, actually, here. Yeah, okay, that's very good. Thank you, Kai. So basically, if we cut them right in the middle, we end up with two magnets. Where we cut, the part that was south stays south, but then where we cut becomes the north. And the other side that we cut it in here becomes the south, and now we end up with two magnets. Okay? Then if we decide to cut it further and further, so we can never isolate monopoles. That is item 2 of the discussion. No monopoles, at least that we have observed in nature, okay? At least that we know of. In the 1950s, there was somebody, at least an experiment somewhere, I don't remember where, in Europe, I think in Switzerland or somewhere, that they claimed that they have isolated the monopole, that they were able to find the monopole, the behavior of monopole. It turns out nobody could replicate that experiment, therefore it still holds true that you cannot have monopoles. You guys get the second question? So the first question was, magnetism and electricity are two sides to the same coin, to the sides of the same phenomenon, per Mr. Maxwell. And the second one is the fact that poles always come in pairs, north and south, okay? The fact that we call them north and south is just a convention, that's all, okay? We could have called this one positive, and we could have called this one negative, okay? Again, that's a convention. We could have called this one, again, we could have reversed the naming. We could have called them south and north. So this is just a naming, okay, just to distinguish between the two poles. As a matter of fact, when you get to for example, we could have called them left and right, although left and right depending on which way you're standing, okay? So we could have called them up and down. We could have called them, for example, brown and black, or we could have called them whatever you want to call them. So basically the naming in here, we could have called them, but just don't get into the idea that this is, as a matter of fact, if I take a compass now, where is my compass? And point it to them, it's going to point toward the north, okay? And where the compass points toward the north is actually the south of the magnet, okay? And vice versa. So you have to understand that. So when the compass is pointing to the geometrical north, that is the south of the magnetic pole of the Earth. So the Earth is a huge magnet, as a matter of fact. So it's a big, big magnet, okay? So that is one thing in here. Then we have field lines, okay? Always, I have another kind of magnet in here. I have a horseshoe magnet. Always, magnetic field, they leave the North Pole, and they emanate from the North Pole, and they converge into the South Pole. And here in the same bar, this is the North and this is the South. This is the North and the South. So everywhere in here, you can find them. And how to visualize them, you bring something called the iron filings, which are pieces of iron that you're going to take, and basically, let me see if I have some here. I think I do. I have a bag in here of stuff, okay? And you sprinkle them on the magnet, and you see which way they will line themselves right with the magnetic field, with the field lines itself. So that's another concept. Let's see in here. Yes. If we're in the lab, you're going to deal with this one. These ones are like sand, but they are not sand actually. These are iron filings. So if I bring a magnet in here, you see them, they follow it, okay? And they follow what? They follow actually the field lines, okay? Because this is not too strong of a magnet. It's not really pulling on them as strongly as another magnet. Let me see if I can bring a stronger magnet in here. This one is super strong magnet, okay? See here? They actually line up with it. So if I remove it, look what happens. They're going to fall per gravity, okay? The whole thing fell per gravity. I mean, they're stuck in here because it's still so strong. And then as I bring the magnet, they will follow it, okay? Again, this will indicate for me, if I do it on the ground, yeah, we're going to do it, okay? If we do it on the ground, they will, if I put it in here, actually we'll see the field lines themselves, how they line up, okay? So let me draw the graph it quickly here. Oh man, this is a super strong magnet. I really don't want it. I want it to stay away from everything. You have to be very careful with strong magnets because they sometimes can, although nowadays the credit cards, basically the magnetic tape on it, usually it sustains a lot of it's not going to be scrambled easily, but in the old days there were powerful magnets could do that, could basically reorient the magnetization of the band, the magnetic tape on your credit card or debit card, and ruin basically your information and try to take it, and it says unreadable. So let me share with you a screen first of all. Let me find it. And let me go into, yeah. So where is the share? Where is it? All windows, OneNote. Let me get into a new tab in here, okay? So I think Taryn is the one who asked to draw the field line. So here is a magnet, bar magnet. This is the easiest of them. I have a north on one side, a south on the other side. The field lines, again, they leave the north and they end up back in the south, okay? So these are the field lines. How many field lines actually do that depends on the strength of the magnetic field, or at least tells you the strength of the magnetic field. So this field line was too big for me to draw. It went way outside and came back. As a matter of fact, there is another one in here similar to it, and it's going to come back in here. There is another one that is going to go straight out in here, okay, from north to south. Closer in here is going to be this way, okay. Same thing in here, by the way. Now, there is another one in here that's going to go in here. And where is it going to come? It's going to come from this side, okay. So this one technically would go around the universe. It's going to go wherever you want it to go and come back and end up in the other side. So the fact that, as I said before, you cut it in half, it's going to really create in here another north and another south in here when you do that. So if you don't cut it, there is no such a thing in there. Okay. Now, when I throw in those iron filings, actually they line up themselves with the field lines. That's really what you were looking at earlier. Okay. So that's a visualization for my. Now, if I bring a needle in here, the needle will point to where the north is. Okay. So this is where the north is. Okay. Or is it the other way around? I think it's the other way around. It's going to follow the field lines. I'm sorry. It's going to point to where the south is. Okay. It's going to follow because if you put a needle in here, it's going to follow the field line. If you put it in here, it's going to follow the field line. Okay. And that's basically the fact that it's pointing to the south pole. Okay. I'm trying to look for my needle in here for my magnetic compass, but I cannot find it. I probably moved stuff the other day. I don't know where it is. Okay. Did anybody see it? No. Okay. Anyway, I wish we were in the lab. We can do the demo a lot of this fun stuff. So again, let me stop sharing that screen and share with you the other screen now. So the field lines, and then we're going to get into the magnetic domains. Magnetic domains is what explains to me what this magnet is all about. Okay, how is it working? Any magnet, as a matter of fact, and how it works, basically. So all magnetism is in the so-called permanent magnets, because these are permanent magnets. Okay, and like this magnet in here, which is really not magnet at all at this point. It's made out of copper, and copper is not magnetic, so it doesn't have magnetic properties. Case in point, this wire is actually copper inside, and it has a protective layer. So if I put this thing in here, it's not going to attract it. It's not going to attract a piece of iron, okay? It's not going to attract another magnet, as a matter of fact, to it, okay? So it's not, that's magnetic at all. So let me put this thing in here. It's not going to attract it. So if we're going to put it in here, oops, it's going to fall. But if I run a current through it, it's going to be a magnet. So let me run a current in here. I have a battery, a 9-volt battery in here. And so basically this is what I'm trying to do in here. I have a 9-volt battery, and I'm going to connect the two ends to it. And this battery still good. This should be magnetic, okay? See now? I don't know if you see the piece of iron that I just put in here. And now it's stuck in there. It's actually, as a matter of fact, it's trying to line up itself in there. Now, if I cut the current, okay? I'm going to cut it in here. It fell, okay? Because this is an electromagnet. And this is actually the same thing is happening with a permanent magnet, except that those currents that are in a permanent magnet are basically they are due to the charges that are moving in the matter itself. Okay, due to the electrons moving around the atoms, and they support one another in a permanent situation. And now you have a magnet. Okay, so this one, the reason why it's a magnetic at all, is because of the same reason as an electromagnet, except that these currents in here, they are due to the electrons inside the charges. And the reason why I'm not electrocuted is because these charges are canceling one another with the positive charges. So there is a permanent motion in here of charges that creates magnetism in the same fashion as the electromagnet, okay? The advantage of the electromagnet over a magnet is that you can control the magnetism of an electromagnet. That's one thing. The other thing also is that you can vary it. That's what means control. You can have as much magnetism as you want and as low magnetism as you want. Okay. Whereas this one is very hard to control. Once it's made, it's made. Okay. Furthermore, you can attain tremendous amounts of magnetism. Okay. You can build a lot of magnetism by running a huge current through this one. So this one is proportional to the current. You saw when I killed the current by basically disconnecting the wire, that hey, this thing become no magnet at all, because it's not really a permanent magnet. It cannot behave as a magnet, but it's magnet temporarily as long as there is a current. The other one is a permanent magnet because the currents now are self-sustained basically within the circuit itself, within the piece of iron itself, or cobalt itself. And here this is a different material. This is actually a stronger magnet than the first one. Okay, it's very, very, very hard to remove. Okay, try to remove it, and this is what happened to it when I removed it the other day. There was another piece attached to it in here, and it has actually a protective layer in here, and the protective layer came out. It was super strong. Okay, so this is a permanent magnet. Even that is not as strong as an electromagnet that you can make in the laboratory. Electromagnets can be super strong. Magnetism is measured in something called Tesla. Okay, that's the unit for the magnetism in honor of Mr. Tesla, who did a lot of work on the electrical currents and actually the alternating currents and things like that. And he was one of the leading figures in terms of power generations and things of this nature. Now, a 1 Tesla is tremendous magnetism. Okay, these magnets that I have in here, these are very, very small. The one that I have another strong magnet somewhere else, but not as strong as the one I was showing you guys. And I don't know where they are right now. Okay, I have other magnets in here, but I don't think that they have. I don't know their values. Okay, these are all magnets actually, and yet I have far more magnets in here. It's really ridiculous how many magnets I have in here. But the point being in here is their values are a lot less than the Tesla. They usually are measured in something called the Gauss, and the Gauss is about 10,000 Gausses make one Tesla. So this is about 400 Tesla, 400 Tesla, that's nonsense. 400 Gauss, 230 Gauss, 500 Gauss. That's very, very small. It's still 0.004 Tesla. And 1 Tesla in the laboratory that's sometime made, or if you go, for example, for the MRI machine, that can generate a lot of magnetism. And that's why the first thing for the MRI machine they tell you is, do you have any metals on you? Do you have anything in there? Because there is tremendous magnetism in there. So if you're wearing any piece with a metal in it, they ask you to remove it because the magnets in there are super strong. Okay, and 1 Tesla, 3 Tesla, 5 Tesla, sometimes even 30 or 40 Teslas for the nuclear accelerators in the laboratory. And I'm thinking in terms of the Betatron, which can reach tremendous magnetism. So that is the unit for the magnetic field. And again, the 2 different kinds of magnets, they are permanent magnets that have very limited applications. Like, for example, in motors, most motors, they have permanent magnets. Okay, the one that you're going to need to build yourselves for physics 11 has a permanent magnet in it. You have to have a magnet. Without magnets, you cannot build a motor. Also, for power generations, you have to have also magnets. Okay, you have to have permanent magnets. But electromagnets, they're heavily used also in the industry and also in technology. Okay, for trains and so on and so forth. Okay. Magnetic force on a moving charge. I mentioned that to begin with. That is basically the fact that if a charge is moving in a magnetic field, it's going to go actually in a spiraling path. It's not going to go straight out, because if the magnetic field is pointing this way and the charge is moving this way, it's going to spiral actually in this direction. Okay, so it says the force is going to be here, so it's going to spiral in that direction, and that's what happened actually to the charges that come from the sun. There is tremendous amount of charged particles that come from the sun, especially 2 kinds: protons, very energetic protons that come from the sun, and electrons that come from the sun. Both of them are charged. The protons, they will spiral and don't hit the Earth into the north or the south pole, okay, depending on their charge, okay, and the electrons, they will spiral in the other direction, because of the fact that Earth has a tremendous magnet. If the magnetism of the Earth did not exist, what happened? All of these charges will hit us. They're coming from the sun, and they're coming also from other cosmic sources, or from other sources from the universe. Because of the magnetic field, we're protected. If there was no magnetic field on Earth, no life could survive that much bombardment. I mean, you wouldn't survive for minutes, let alone for thousands of years. Okay, I mean, life itself will not. So it's not just the humans that are going. Plants and animals we cannot. So it's billions of years now since life existed on Earth, and it's basically safeguarded by this magnetic field due to the Earth, and because of these charged particles. There are two belts that are basically surround the Earth, the so-called Van Allen belts, and one of them is basically traps the negative charged, and they're super light. Okay, they're trapped first, and then the others they're trapped second, and those are the two belts. Sometimes there are other belts that form in the Van Allen, but most of the time it's only these two. And these are super basically needed for the protection of life. When planetary missions when the astronauts try to leave Earth, they really have to go super quick on these belts because they themselves also will be exposed to the large amount of radiation that is basically being pushed to the North Pole or South Pole. So there is an angle with which they have to travel in order to avoid to be basically exposed too long for this radiation, because it's deadly, it's really fatal. Okay, so and then we're gonna, because currents in a wire, they are actually carrying charges that move. So now there is a net effect of the magnetism on a wire that has currents in it, and basically it will bend the wire. Okay. I already mentioned the fact that the Earth is a big magnet, and the magnetic field of the Earth actually is needed for the protection of life, and also how some living organisms basically respond to the magnetic field. So this is in a nutshell what magnetic field is, what magnetism is, what the chapter is. Any questions? You can go home now. Actually, you guys are home. Okay, so let's delve into a little bit more details. Okay. So again, the term magnetism comes from a mountain near in Greece called Magnesia. Okay, their unusual stones were found by the Greeks more than 2,000 years ago. These stones, called lodestones, had the intriguing property of attracting pieces of iron. Magnets were first fashioned into compasses and used for navigation by the Chinese in the 12th century. Okay. Do you guys know the story of how magnetism was actually discovered? Does anyone know who discovered magnetism? Okay, I'll tell you the story that I heard myself. Okay. This is by my thesis advisor. Okay, and a group of people who were sitting about it, and they said that this lady in you know how the story of the what is that guy, the tall guy with one eye in Greece? Do you guys know him? He's 5 feet. No, not five. He's what, 10 feet tall or something like that. Or he has one eye in the middle. Anyone had Greek? Okay, yeah, I think that's the one. Okay, does everybody know what that is? Cyclope? Okay, very good. So this guy apparently was devastating the city near Athens, and he was basically coming and eating the children of the people. So this lady, apparently, this is the one who discovered actually magnetism, was sick and tired of it. So what she did one day, she took this rock because she knows about the properties of it. She wrote the phone number of the police and she pasted it on the refrigerator so that next time when the Cyclope comes in, she would call the police. So that's how magnetism was discovered. Yes. It was discovered by this lady who basically took this rock, wrote the phone number for the police so that when the Cyclope comes in, and put it actually on the refrigerator to call the police. That's why we use magnets in our refrigerators. Does this make sense, the story? Do you guys believe it? What's wrong with it? Kyle is doubting my story. Anybody else is buying the story? Come on, guys. What's wrong with the story, Kyle? Come on, guys. You guys are awake or asleep in here? I know it's only 4:30. Okay. Obviously, I really don't know the story of how nobody knows, actually. The person who told us this he didn't know how magnetism was discovered. So I have no idea myself also. So that basically people knew it for a long time and nobody can trace it back to a single person. Okay. But it's an interesting story. Okay. What's wrong with the story? Can anybody tell me what's wrong with it? What's wrong with it? Where did I go wrong? I have so many people in class in here. Okay. Was the story have to do with the phones or the refrigerators? Okay. Okay. When we are in class and tell this story to my students, they sometimes are, because they had to spend a little bit of drama, build a little bit of basically hype around it, and at the end, the minute I mention telephones and also refrigerator, that's when basically they don't like that, because they know refrigerators and telephones were not invented in the time of the Greeks. Yet for some reason they don't object on the Cyclops, on a person who was 10 feet or 20 feet tall and with one eye. That's fine. Okay, so that's the problem with the story. Okay, again, this is basically in a nutshell what we know so far. Okay, the main thing is not that. Okay, the force between any two charged particles depends on the magnitude of the charge. That's what we know. Okay, this is the electrostatic force that we discovered a long time ago. When the charged particles are moved with respect to each other, the electric force between the charged particles depends also in a complicated way on their motion. So there is a force due to motion of the charges that we call magnetic force. So that's what we know, that this magnetic force is actually when charges are in motion. When charges are not moving, then in this case, what we have is electrostatic force. So if I have a charge and a charge, they attract each other because they are stationary. When they move now, they react to one another because of their charge, and also they react to themselves because of the magnetic force. Let me give you a hint into why the early statement that the fact that magnetic field and electric field are related. Magnetism and electricity are related. If a charge is moving, it creates a magnetic field. We know that for a fact. Okay. So we have magnetism because the charge moves. Okay. That's because the currents I did earlier in here. The current is charged in motion, creates a magnetic field. Now imagine for a second, okay, and this has nothing to do with the story before. This is actually a thought experiment. Imagine somebody who actually lives on the planet charge, on the planet, for example, electron, okay, tiny particle that lives in there. From the vantage point of the electron, everything else is moving, the electron is stationary, okay? From a vantage point of something that is on the charge itself, the charge is not moving. For example, right now we're sitting on the earth, we think that the earth is stationary, everything else is moving. If you're sitting in your car and you're sipping your a cup of coffee, for you, the car is not actually, it's the ground that is moving, because a cup of coffee, as we can look at it, or the water next to you, the level of it is stationary, especially if you're driving with cruise control and the road is smooth. So if the windows are locked, closed, and you're moving with uniform motion, you wouldn't tell, okay? And if when you open the windows, and if there is no cultural, basically, bias, you wouldn't really know that you're actually the one moving, except the ground that is moving. Same thing in this situation. So from the vantage point of the charge, everything else is moving. So we're back to the stationary situation again. And how can we explain then interactions with other charges that are basically due to magnetism? Okay, since there is no magnetism in here. Magnetism depends on the charge in motion, but from the vantage point of the charge, there is no motion. So in this case, to explain that interaction, we introduce the electric field. So it's actually interacting through an electric field. That's why we had to invoke the other one. So electricity and magnetism are related through this connection, and this is the so-called relativity, basically. Okay, when two cars basically are incoming to one another, the relative speed is higher than if they are going in the same direction. As a matter of fact, you can exchange phone numbers if you're moving with the same speed to somebody else next to you, even going 70 miles an hour. But if you're in the same road, the same direction, then your speed is the same. Okay. So force of attraction or repulsion between a pair of magnets depend on which one end of the magnet is held. That is a common knowledge that I showed you earlier. Behavior is similar to electrical force. The strength of the interaction depends on the distance. Of course, it depends on the distance. If I put them far away, I can hardly measure any strength. The closer I get them together, the stronger this force is going to be. Let me put them so that I can repel them. So at this point, I don't feel much repulsion. But once I get them close, it becomes harder and harder to the point that it becomes almost impossible for me to put them next to one another. Actually, as a matter of fact, I have to exert a lot of force to put them next to one another. And the next possible way for them, they repel one another. So this is because of the repulsion. It's very hard to do it, okay? And you guys, if you have magnets, you can do that. Now, if I put them back in the opposite direction, the closer I get them, the harder for me to keep them apart because they will be actually attracting one another, okay? So they attract. Now I have to really exert a lot of force, and as they move away, the force becomes weaker and weaker, okay? So it's inversely proportional to the distance, okay? And it increases with the distance when they're closer to one another, okay? Where is my SharePoint in here? So magnetic poles give rise to a magnetic force. Two types interacting with each other. You have the North Pole, north-seeking poles, and South Pole, south-seeking poles. The rule of magnetic force between like poles repel, opposite poles attract. Again, these are the field lines I was showing you earlier. I was drawing earlier. And you use something called iron filings in here, which are pieces of iron, actually, that line themselves with the field lines. And you're going to see you actually visually look at it and see it. When we do this experiment in class, the students usually take pictures with their phones because it really makes a beautiful imagery. And here, I really don't have a lot of iron filings, but they make a lot of nice, basically, features for that. So a weak and strong magnet repel each other. The greater the repelling force is by whom? Who repels the most? So if I have a weak magnet and a strong magnet, okay, let me put them in the opposite direction, okay? Right now they are repelling one another. Who repels the strongest? What do you guys think? Is it the weak magnet repels the most or the strong magnet repels the most? Jeffrey thinks it's the stronger. Why do you think the same, Samantha? Can you give me a reason why? There is this one strong, this one is weak. And I put them so that the poles are similar in here. So this must be the South Pole. And you're telling me that they repel the same. I must get them in. Because force exerted on an object is the same from both. Which law is this? It has a name. Do you know it? You remember it, I should say? Whose law is this that says that they have to be the same? I mean, you're right. They're the same. Actually, I can feel it the same on my both. The third law of Mr. Newton. That's beautiful. That's the law that we need to invoke in this case. Okay. So it's the third law of Mr. Newton is the one that dictates that the two forces must be the same, regardless of which one is weak, which one is strong. Okay. Because they are interacting, And if one exerts a force on the other exerts a force that is equal in magnitude and opposite in direction. Same thing holds true, by the way, for the attractive force between the different signs, different poles. Okay. Regions of magnetic influence surrounding magnetic poles. So that's the magnetic field, basically. So what the magnet does then around it, it changes its surrounding. This magnet actually modifies this entire area near it, including my hand, by the way. Now, if I bring a piece of iron, for example, that interacts with it, it can interact with it even through my hand. Okay? I have the magnet now in my hand, and look. Okay? So basically, the magnetic field lines will cross my hand. As a matter of fact, you can clearly see. If I remove the magnet, watch the iron in here. Okay? So again, the magnetic field lines are going through everything, okay? To the point that they can penetrate the hand from the inside out. They change the entire environment around it, okay? Believe me, this is safe, okay? So this is not really, it's not going to damage the atoms in my hand or anything like that, or the blood in my hand or anything like this. But if I remove the magnet, bang, there is no magnetic field now, okay? So if I try it with the weak magnet, it's not going to give me a good effect, okay? Let me try it, because the magnetic field will, the weak one will create, those are two of them, by the way, okay? But they're not, as a matter of fact, it's trying to seek the lowest points in here. So let me put them very close from it, okay? No, it's not sitting still as the other one is. Yeah, it's not really sitting still as the other one is. As a matter of fact, if I get even a weaker magnet, this is by itself, okay? It's not sitting still. So this one also modifies its environment, but not as well as strong magnet, okay? So that's what we mean by magnetic field. The magnetic field is the one that when I put the magnet in here was going everywhere in space, including through my hand and out. So the piece of iron in here was attracted to the magnet. And I can tell using a magnetic compass or using a iron filings, I can see the exact field lines. By conventional directions from the North Pole to the South Pole produced by the motion of charges in atoms. So here is a visual of this. So this is an iron filings actually, okay? And the denser the field lines, the stronger the magnetic field, okay? In an atom, what's going on in this case, you have the electrons moving around the nucleus, okay? And that is equivalent because every period they complete one cycle. One period they complete one cycle. And the charge in this case is the charge of the electron going once, and they go super fast around the nucleus. So now that is a current, actually equivalent to a current. But also there is another phenomenon in quantum mechanics where the electron actually goes around its own axis, okay? Or at least that's the visual that we have. We really don't understand it very well, to be honest with you, to say that actually this is how it is. But to visually see it classically is as if the Earth spinning around its axis. Of course, the electron is a point in space, so it doesn't really have dimensions to really be doing that. But the electron itself has an internal motion or an internal property called the spin, in addition to the fact that it's rotating around the atom. These two phenomena create the magnetic field for per atom. Now, most of the electrons, the inner electrons for the atom, they're actually canceling one another. So they average to no magnetism. It's only the outer electrons that have the possibility to do that, okay? Especially if they're isolated or they're an odd number of them. Then in this case, they can end up with being a net current, if you wish, for that specific atom. And the atom will have a magnetic field in this case, okay? So not all elements have this property. Not only that, but only 3 elements, they can actually retain their magnetism after you cancel the magnetic field. And those elements are iron, nickel, and cobalt. So that at least the elements in terms, those are the only ones that can be so-called ferromagnets. In other words, retain their magnetism after you cancel the applied field. Other materials, no. Once you cancel the applied field, the atoms go back to basically to their random motion. Some of them, they have their magnetism going this way, others going this way, and at the end there is no net magnetic field when you remove the magnetic field. Only iron, cobalt, and nickel, they have this. They can help one another basically and retain their magnetism after you cancel the magnet. We are running out of time, so I really have to expedite this thing, and I really don't know where we are on the slides. We are way... Okay. So the source of all magnetism is electrons rotating around an atomic nucleus, yes. Electrons spinning around an internal axis, yes. So both, either or both, A and B, okay? That doesn't make sense. C. So the correct answer is C. Where magnetic fields are more dense, then that's where the field is the strongest. So the correct answer is B. Now, really, in order to understand magnetism, you have to do something else. Let me come back into this. Let me first of all stop sharing that screen and share with you this screen to understand what the magnetic domains are. Okay. So think of the atom again. I'm going to take the case of, come on. If I take an atom in here, okay, and let's say, for example, the motion of the electron that is responsible for the current. This atom, for example, has its electron moving counterclockwise. So I have an electron in here moving this way. So it's going in a circular path. If I take the next atom next to it, it's also, for some materials, is going to have its electron moving in the same direction. Actually, these 2 electrons will influence one another so that both of them will be moving in the same direction. The next neighbor also will have its electron moving in the same direction. This neighbor also will have its electron moving in the same direction. This neighbor also in the same direction. This neighbor in here in the same direction, and so on and so forth. All of these atoms, they're moving counterclockwise in the positive direction of motion. Okay. In this region, this electron is coming this way, and the other one is coming this way. So they cancel. The 2 currents in here, the net currents are 0. This one is moving this way. This one is moving in the opposite direction, and they cancel. The same thing is happening in here. This electron is moving this way, and this electron. So wherever they join, they cancel. This one is moving down. This one is moving up. This one is moving up. This one is moving down. Okay. The only thing that I see in this thing is the outer electrons. The outer electrons, as if when it meets to this point, it continues to the next point. So as if there is a continuous current in this region that is moving counterclockwise for the entire region. So as if I am back to this picture. I have a net current moving in one direction when I applied the current earlier. So I have a magnetic field that is perpendicular to the current. So the magnetic field in here will be coming out of the screen. So it will be coming out of the screen. So think now that the entire material, magnetic material, is made up of these regions in it called domains. So there is a domain in which the magnetic field is pointing this way. There is another domain that is the magnetic field is pointing this way. There is a domain where the magnetic field, and they are not necessarily the same size, by the way, or not all the same direction. Okay. So they could be random domains, and that's what is going on with most materials, okay? But in a magnet, in a permanent magnet, they line themselves more or less in the same direction, okay? So we have a net magnetization or net magnetic field that is pointing in one direction. So that is then where the south is, and that is where the north is. So this is how magnetism can be explained, and there is this inner charges basically that move through their atoms. At this point, I really don't have current. When an electron moves around its atom, there is not a current, but I can assume it's a tiny current. But these tiny currents in a regional space, in a special material, they work together to become a net current in an entire region called the domain. So this is now a domain. This one is another domain. Okay, So that is basically how these regions in space are working. Now, when domains help one another, so this domain will help this domain to line up, and this domain will help the other domain to. It's basically like people leaning on each other to stand up, okay? That's basically what they're doing. So who is supporting who? Both of them are supporting each other. I am supporting my friend so that he doesn't fall, because if I move back, he's going to fall. And he's doing the same thing. So we're leaning on each other to basically stay in line, stay up, okay? If one of us decides, no, we're not going to do it, the whole line basically comes down. So basically, imagine a bunch of people standing next to each other, and of course, they're not using their hands, they're leaning on each other, and basically that's how they are. This is leaning on each other. They call it in solid-state physics self-consistent solution, meaning that they help one another without the need of an external field to help them lean on one another, okay? So this is how magnetism works in a permanent magnet, okay? It's through these tiny currents in different regions in space that are called magnetic domains. And they're in this picture in here with these arrows, okay? So magnetized clusters of aligned magnetic atoms, that's what a domain is. Permanent magnets made up by placing pieces of iron or similar magnetic materials in a strong magnetic field. So first of all, we have to put them in the strong magnetic field, and then strong materials with a magnet to align the domain. So once they're aligned, once you remove what caused them to align to begin with, they rely on each other to stay in the same direction, okay? Other materials don't do that. Non-ferromagnets, they don't do that. As a matter of fact, like this one, for example, right now, it's not a ferromagnet, it's not a permanent magnet, it's a ferromagnet, but it's not a permanent magnet. When I remove the magnetism, is going to stop, basically, it's going to come down. So this is actually a different material, which is called the paramagnet, okay? So permanent magnets, alignments of domains remains once external magnetic field is removed. Temporary magnets, alignment of domain returns to random arrangement once the external magnetic field is removed. And then this is the idea I was talking about earlier for cutting the magnets. No, you cannot isolate them. It turns out a wire can create a magnetic field too that has a current passing through it. This is the so-called Ampere's law. It explains to us how magnetism is formed. So magnetism, or magnet, and magnetism can be created by a wire carrying a current. That is the essence of electromagnets. Okay. So again, how is that? If the current is running with your thumb, the current is your thumb, the magnetic field is with your palm. The way your palm curves, it curves with it, okay? So it goes around it. So if the current is going this way, so in this case, yeah, this must be going this way. So that is how this current is coming, okay? So it's always going, following the right-hand rule. It has to be your right hand. It cannot be your left, okay? So if you're left-handed, you're out of luck. Okay, so this is your current. This is where the magnetic field goes. Okay, it follows how the palm curves around the thumb. These are different currents. Also, we've put iron filings. Also, they form this beautiful geometries for it, indicating which way the magnetic field is. This is an important application in industry called the solenoid, similar to this one actually, where there is a wire in here which has current running through it, and the magnetic field is going to go right through the middle, just like this one actually, right through the middle of the magnet. Okay, so that's exactly how the magnetic field would work in this case. Electromagnets are used in industry a lot. Like I said, among other things, they're used in trains. You have to levitate the train. You have to lift the train. So trains in Japan and Europe that use this technology, actually, they don't go on rails. They're flying because there is a small separation between them and the rails, And while they're moving that way, they can reach tremendous speeds because there is no contact between them and the rails. And like classical trains that really require that contact and friction to get going, this one they use electromagnets actually of the same polarity, so that they remain in suspended, and then actually they are accelerated also with magnetic forces too, with the electrical currents and the wires up, so they can go actually tremendous speeds. Okay, the only limitations for it is safety actually concerns, and you don't want to especially when you're going around curves and things like that. That's why they have this aerodynamic shape, so that they minimize the air resistance, because they're like planes really. They are flying. Okay. So an electromagnet can be stronger by, no problem. So an electromagnet can be made stronger by increasing the number of turns in a wire. That's one way, because you'll have more and more magnets. So that's why you see this one wrapped with a lot of basically turns. Okay, there's a huge number of turns, because each and every one of them acts like a small magnet. Okay, see them? I don't know. It's trying to focus on me, this camera. I hope that there is a way to turn the focus quickly. Okay, each and every one of this is actually a wire, and that's why when you're trying to build your motor, you have to be careful in how many wires how many turns you can make. Okay, it depends on that. Okay, and also it can increase the current. That's the other way too. Okay, this one actually they had to wrap it around this thing in here. I never opened it. Oh, I don't want to open it. There's so many wires in here. Okay, to really do the same thing. Again, it's both A and B. So you can increase the number of turns. The turns are loops. I think in the lab we call it loops, and or increase the value of the current in it. So a current carrying coil of wire is an electromagnet. Okay, strength of an electromagnet is increased by increasing the current through the coil. You have a higher current, you will have a stronger magnetic field. Increasing the number of turns, this is actually what you saw. I don't know if we did this experiment. Yeah, we did. In the experiment, we increased the current, the voltage basically across the battery, and we saw higher and higher currents, and the magnetic field gets stronger and stronger in the same points. That was one of your conclusions for lab. Again, I'm talking to physics 11 people. Okay. And also increase the number of turns, also vary the number of turns, and you saw the strength of the magnetic field also changes with it. And the more they are, the stronger the magnetic field. Also, what you could do, you can induce stronger magnetic field by having a different permeable material. You have actually a piece of iron, for example, in there that enhances the magnetism. That's why most of the transformers, they have this, they run around a piece of iron to increase the flux of the magnetic field, because there will be a stronger magnetic field inside. Okay, in a permanent magnet, you really don't have control over the strength that much. This is levitation. This is using superconductors, because superconductors, they have this weird behavior that they expel the magnetic field from within the material itself. And if you put material like a magnet above them, the magnet is trying to push the magnetic field lines, but they cannot penetrate the superconductor. So in this case, there is like a repulsion with it, and now you have a suspension used. You have levitation used to this phenomenon. Superconducting materials. If my hand was a superconducting material, and you run, that's why you see this. It has to be super cold to do this experiment. It's going to repel the magnetic field, and this piece of iron will not really feel it. Okay, that's the so-called Meissner effect. So again, I mentioned from the beginning that the magnetic field can have an effect on the charges, and this is exactly why we need the magnetic field of the Earth to basically spiral the positively charged and negatively charged toward the North and the South Pole, to basically because that's the motion that they will end up with. Okay, and since the wire itself is actually made up of I mean, when it's conducting electrons, when it's conducting charges, the charges now will be subject to the this magnetic force, and the wire will bend actually because of the presence of the magnetic field. Current is no more than charges in motion. So since the magnetic field involves charges in motion, then it's going to influence also the wire that has a current running through it. Let's again, depending on which way the current will go, that's what the bending is, okay? So this is depends on the direction with which the current is flowing. Okay, this thing in here can be used in devices like this one, actually, for example, to measure the current or to measure the voltage in a circuit, because if you have a coil in there and if you have a strong current running through it, it's going to induce tremendous amount of magnetic field, and that will bend the wire one way or the other, okay? And this will be a reading directly to the strength of the voltage in this case, or the strength of the magnetic field, the strength of the current, okay? So one or the other can be used to determine basically the strength of the current. So this is actually the principle behind the voltmeter and ammeter, okay? Because once you run a current through it, it's going to have a magnetic field, and if you have a magnet in there, it's going to interact with the magnetic field that is induced in the wire, and that's how you have basically an ammeter and voltmeter. And it's also behind the concept of electric motor, and that was the principle for you guys to work on it to do the project. Basically, you have a permanent magnet, you run a current through the wire, and the wire now will start to try to align itself because it will have a magnetic field itself, and there is a torque in here that is going to be created between the permanent magnet and the wire carrying the current in this case, because it has a specific area, so it's going to try to spin it. The only problem with this one are two things. First of all, you have the gravity. If the wire is too heavy or there is a problem, so it may not run as, in other words, the torque due to the magnetic field may not be strong enough, or you may have a lot of friction in it also to slow it down. So when you're building your motor, you have to be keen to this idea. I know I demoed that when I built the motor for the physics 11 class, and it's not hard to build actually, and I'm hoping that some of you guys will actually go ahead and build the motor. Again, I mentioned the fact that the Earth is a big magnet, and where is the current for that? The current is coming from the inner core of the Earth. The inner core of the Earth is made mainly of iron, basically, and nickel. And those materials are super magnetic when they are in motion. They have current, actually, because it's so hot that they are ionized. And now you have ions in motion, okay? And that is current. And that's how the Earth got its magnetic field. For example, the planet Mars, we believe now that it doesn't have as much heat in it, and that's why it does not have a strong magnetic field in it. So Mars is really unprotected in terms of magnetic field. It has super weak magnetic field compared to the Earth. Venus, on the other hand, does not have also a magnetic field, although it has the same heat inside like the Earth. But the problem with Venus is that it spins super slow. The day on Venus takes half a year, basically. Super slow. So it's not good enough it doesn't have a strong magnetic field. And these are the two regions of the Van Allen belt that I was talking about in there, in terms of how they trap the charges and they dump them into the North Pole and the South Pole, depending if they are positive protons or negative electrons. Okay, if you are into the people who, I mean, if you watch YouTube a lot, you will see some people they're raising doubts about whether or not we actually left the Earth atmosphere because of the Van Allen belt, and it's not a problem because actually the shape of them will allow that there is an escape route that we can take. And not only that, if you don't stay there for too long, you're not going to be, no problem is going to happen to the astronauts. Okay. As a matter of fact, they took with them, at least when they went to the moon, counters for the radiations, and they found that they were not exposed. Actually, we are more exposed to radiation than they are when they went to the moon. Again, these are the so-called northern lights, or the aurora borealis, and in the south it's called the aurora australis. And they are as they hit the lower levels of the atmosphere, That is basically when this lights basically of these charged particles basically make this beautiful lights in the atmosphere. Okay, so this is in a nutshell. I talked about some of the pigeons and other basically living organisms that seem to be sensitive to the magnetic field. So this is in a nutshell chapter 24, I believe. Okay, so I'll see you guys on, so we have 2 questions today. So I see you guys, for those who are sitting in physics 11, in less than an hour. For those who are sitting in physics 10 only, I'll see you guys next week on Tuesday. Okay, I'm gonna stop the recording now.